Hello everybody, today we are going to take a look at graphing square root functions. So we've been talking about solving, we've been talking about how to simplify roots. Now it's time to take a look at what the graph of something that has a square root in it, what does it look like? What kind of graph does it make? So you need your foldable today as well as something to write with, maybe a calculator. I'm not really sure if you really need it. We're just going to be plotting some dots, right? Plotting some points. But this little, the front cover here gives you sort of a preview of what this graph is going to look like. It's not a line, it's not a V, it's not a parabola, it's sort of this swoosh to the side, if you will, from one single dot and it kind of shoots outward. So this is the foldable we're working in. The front should say graphing square root functions. You fold it in half and then the problems that we're going to do are on the inside. So just plotting points today, but how do we get those points? That's where this video comes in. So let's take a look at what's called the parent function on the inside. The parent function is just another name for a generic sort of equation where it has a square root in it in our case, because we're talking about square root functions. There's no other numbers, just an x, just a y, and then we would make a table of values to help us graph this. So let's choose some values for x here that we'd want to plug into this equation. Well, just like when you first started graphing lines, maybe we try -1, 0, 1, 2, so on, okay? Well, what happens if you plug in -1 here? If my x value is -1 like I chose, if I plug -1 in right here where that x is, x being -1, what's the square root of -1? There isn't one, right? Oh, if there isn't one, it's imaginary. It doesn't exist. So there is no y value that goes with that -1 for the x value. Well, what about 0? What happens if I change that x into a 0? What's the square root of 0? Just 0? I like it. What about 1? What's the square root of a 1? Just 1. Now what if I try to plug in 2? What's the square root of 2? That's not a pretty number, right? It's 1.41-ish. That's not going to work out real nice. So 2 is not really a nice one to try to plug in. What about 3? Is that going to be a nice one to try to plug in? Nope, I don't know the square root of 3. But 4 is a nice number I could try to plug in here. If I change that 2 to a 4, what's the square root of 4? 2, right? So I would get my x being 4 leads me to a y value of 2. So these are some points, just 3 dots here on this parent function we need to graph. It would look like this: 0, 0, whoops, 1, 1, and 4, 2. So my parent function starts at 0, 0, right at the origin. Woo! And he kind of swooshes out or curves out that looks just like that. Okay, he has an actual starting spot. There's no arrow on that end because there are no values where I can square root negative numbers. I can't square root -2 and so on. So he literally starts at 0, 0 and kind of comes out of that point. Now, if I was going to describe the domain and range of this thing, I would be looking at the x values, remember, for the domain. The range is the y values. So notice right here, this very starting point here, what x value is that right there? 0, right? So the domain starts at 0 and continues on all the way on the right-hand side here to positive infinity. So from 0 to positive infinity is my domain. Or you could say my x values are greater than or equal to 0 if you want to say it like that. My range is my y values. This starting spot is kind of the marker. What's the y value that starts right there? 0. And then it keeps growing upwards, right? These are positive y values up here. This graph would just keep growing up and up and up. So the range is going to go from 0 to positive infinity as well. Or you can say my y's are greater than or equal to 0. So domain and range description are coming back. They're still a part of all the graphs that we do to describe those x values and those y values. So once we know what the general form of a square root graph looks like, then we can just use the clues in an equation to help us graph. You've heard this part before, right? The clues in the equation tell us where to put the points. This is the way we've graphed everything this year. So vertical stretch or shrink, making the graph taller or shorter. That is going to be determined by this number in front here. The number in front of the square root is not the slope of the arms like a line, but instead it makes the graph taller or less tall, short, based on what number is in front there. It could also be negative, which might reflect it over. Now, inside the root sign, just like when it was inside the absolute value or inside parentheses when we were talking about quadratics, this is the part that shifts me left or right, the horizontal shift, the moving left or right for the points. And the number outside here moves it up and down, the vertical shift, the up and down movement. We can use all of these same shortcuts to help us make graphs, and that's what I want to show you how to do right now. So let's look at example 1 there. We're going to sketch the graph of this lovely guy right here. 2 times the square root of x plus 4 minus 3. Now, rather than plug in a bunch of points and hope for the best that we can find out where this graph is located, let's start and draw this in your margin with me. Let's start with points that are on the parent function. That's a funny A. The parent function, again, had 0, 0, 1, 1, and 4, 2 as my coordinates or my points. This was in that table that we made for the parent function. And I'm just going to draw a little mini table there. Okay, now when we look at those parent points, that's the general equation. That's the general form. What happens to it happens from that general form. So looking at this equation right here, there's a 2 in front. What does that mean? That means he's going to be stretched vertically up and down 2 times taller. So he's going to be stretched vertically 2 times taller than what he was before. So I'm going to make another little table here to account for my stretched points, if you will. What happens after I make this graph 2 times taller? Well, my 0, 0 point. 0 is still the x value. That's not a tall measurement. That would be the y value. So if I make the y value 2 times taller, if I take this y value times 2, does it change? No, it's still 0. What about 1, 1? Now he becomes 1, 2, because I multiply that y value by 2. Now 4, 2 becomes 4, 4. I'm multiplying that y value by 2. So I've now found out where my stretched graph goes here, and I can plot that here on this graph. This is not my final answer, mind you, but this tells us where we're at this point. This graph is stretched 2 times taller than the original parent graph was before. Now from those points, after I've figured out where my stretch is, now I can shift it left or right. What's this telling me to do? This is telling me to move to the left 4, and this guy is telling me to move down 3. So each point that I've just graphed on my stretched graph here needs to follow that step. I need to go left 4 and down 3. So I'm just going to start with my 0, 0 point here. Left 4, down 3. 1, 2, 3. Here's his new location. Left 4, 1, 2, 3, 4, down 3. 1, 2, 3. New location. Left 4, 1, 2, 3, 4, down 3. 1, 2, 3. And there's the new location. So each point on that stretch graph moved to this new spot, making this graph right here my final answer. So my final sketch for what is the equation y equals 2 times the square root of x plus 4, subtracting 3, okay? So looking at that graph then, what is the domain? What are the range values? The same questions we asked about the parent function. So let's look at the starting point right here. What is the x value right there? It's at -4. So my domain goes from -4 to positive infinity. That arrow is pointing there on the right-hand side, going to keep going and on forever. My range is my y values. What's the y value down here at this point? The y value is -3. So -3 to positive infinity. Or you can say x is greater than or equal to -4, y is greater than or equal to -3. Okay, that's how we use the clues within there to change the parent function to find our new location. Let's take a look at another example. Example 2, we're going to start the same way with the parent graph. Those are the points we're about to shift. We're about to make them move. 0, 0. What else was in there? 1, 1, and 4, 2. Now what's in front there? Is that a stretch, a shrink? What's that doing? That guy right there is a negative sign. That's telling me I'm going to flip him over. Okay, to reflect him over the x-axis. So instead of being 0, 0, well, it's still going to stay 0, 0, right? Can't really flip it over 0. Now, what about 1, 1? Now it becomes 1, -1. and 4 positive 2 becomes 4 negative 2. So once I know where my new reflection graph is here, 0, 0, 1, negative 1, 4, negative 2. Here's my reflected graph. Notice it's swooshing downwards this time. Nice. And now I'm going to translate or move or shift my points according to the rest of my clues here. What's this telling me to do? I need to go to the left 2. What's this guy telling me to do? I need to go up 4. So each point on my reflected graph here needs to move that description, left 2, up 4. So left 2, 1, 2, up 4. 1, 2, 3, 4. Here's my new point. Left 2, 1, 2, up 4. 1, 2, 3, 4. New point. Left 2, 1, 2, up 2, 3, 4. 1, 2, 3, 4. There he is. This was my starting spot. Swooshing downwards like so. This guy right here is my final answer. So what's the domain of that final answer? What is the x value that starts right here? That's negative 2, and the arrow is still pointing to the right there, so negative 2 to positive infinity. Now my range, my y value right there is 4. 4 to what? Notice how the arrow now is not going up at a gradual ascent, it's now going down. So this is 4 to negative infinity, or we would write negative infinity to 4. You may also say my y values are less than or equal to 4. And just like here, you could say your x values are greater than or equal to negative 2. If you want to write it either way. You don't have to write both, but either way. So example 3 and the last one in your notes here for square roots. Let's take a look one more time at the parent function. 0, 0, 1, 1, 4, 2. What's this going to do when we take a look at that number in front here? There is a stretch, but really he's kind of a shrink, right? Because we got a 1/2 here, so we're talking about a shrink, there we go, of those points. So 0, 0 is still going to stay the same, because even if you multiply 0 times 1/2, you still get 0 here. But 1, instead of being 1, 1, it's now 1, 1/2. He's half as tall. Instead of 4, 2, he's now 4, 1. He's half as tall as he originally was. That y value is now in half. So my shrunken graph here, 0, 0, 1, 1/2, 4, 1, see how he's half as tall as the original. Very gradual. Now from there we can move our points according to the description one last time. This is to the left 3 and down 2. So this point goes to the left 3, 1, 2, 3, down 2, 1, 2. 1, 2, 3, 1, 2. And last one, 1, 2, 3, 1, 2. And I now found the new location of my square root function here. Let's do domain and range. Domain, this is my final answer. I'm going to label him so we don't get confused. My final answer here, negative 3 is my starting x value to positive infinity for my domain, or you can say x is greater than or equal to negative 3. And my range, what's my y value right here? Negative 2 to positive infinity, or you can say my y values are always greater than or equal to negative 2. Okay, so now we've taken a look at how to use those shortcuts to make this same graph over and over and over. Sometimes you have a shrink up here, sometimes you don't. Sometimes you can just graph the parent and then shift it left or right based on the rest of the description. Okay, so use the clues, make good graphs. Thank you for taking good notes. Kincaid out.